Hi, good afternoon. Welcome to Embedded Testing Conference, a Menlopark initiative. This is Rohini Krishna, Operations Manager at Menlopark Technologies. Our next session, which is a case study that would be presented by Dr. Roberto BAGNARA from Buxing. As part of this discussion, Dr. Roberto will highlight on a concrete case where a statement of MISRA compliance was done. Menlopark Technologies is a leading provider of embedded hardware and software products to automotive, automation, and aerospace industries across the globe. Our engineers can advise you on the best product set to suit your technical and business needs. And we offer product configuration, bundling of hardware and software solution for hassle-free product development. The presenter for this session is Dr. Roberto BAGNARA, Chief Technical Officer and Chief Scientist at Buxing. He is also a full professor of computer science at the University of Parma. He co-authored more than 40 papers in international journals and conference proceedings on programming languages, static analysis, and other techniques for software verification. Roberto will continue the session now. Over to you, Roberto.
Okay, so welcome to this case study. In this presentation, I will recall what is MISRA compliance for, and I will present some experiences we have gained with our now more than 10 years of work with the industry that uses software for safety critical projects. And then I will illustrate some key features for MISRA static analysis accuracy, and then I will draw some conclusions. So let's start with what is MISRA compliance for? The C language has several good, strong points, which are countered by matching weak points. For example, the ease of writing efficient compilers for C for almost any architecture is the same reason why we have non-definite behavior in C. So the semantics of the C language, and the same thing is true for C++, is not completely defined. The fact that it is possible to write efficient code in C with no hidden costs is because there is no runtime error whatsoever. So the fact that we have many compilers for C and also for C++, and that these languages are defined by ISO standards, and the ISO working group standardized existing practice, is another reason which is causing non-definite behavior. When we have two or more compiler vendors that are doing the same thing in different ways, the only way forward in standardization is make the thing compiler dependent. So not completely defined, and let implementations choose the behaviors. The fact that it is easy to access the hardware is the same reason which is the cause of the facility with which it is possible to corrupt the program state, for example, overwriting the stack. And it is possible to write compat code in C and C++, but for the same reason, the language can be easily misunderstood and even abused. So several features of C are in sharp conflict with safety and security requirements. The solution that industry has identified is called language subsetting. So you don't program in C, you program in a subset of C where the possibility of committing potentially very critical errors is much less. And language subsetting is mandated or recommended by all safety and security related industry standards. And the most authoritative language subset for the C programming language today is MISRA C. So I will focus on MISRA C in this presentation, even though many of the things I say are true also for MISRA C++. Here is a picture illustrating briefly the history of MISRA C and of MISRA C++. In the beginning, we had Ford and Rover that were working at their own internal coding standards for C. They joined forces in the setting of the MISRA project, and in 1998, they published the first edition of the MISRA C coding standard. And as you can see from the picture, the MISRA C coding standard has influenced almost all coding standards that have been proposed for C and C++ afterwards. So the application of MISRA guidelines typically are one requirement in a contract. In this contract, there is the acquirer, that is the organization commissioning the project, and the supplier, the organization developing the code. And both organizations need to cooperate in the task of assuring compliance with respect to the MISRA guidelines. And it is much better if they negotiate what is possible to negotiate in MISRA compliance at the very beginning of the project, even better before the project actually begins. So what is MISRA compliance for? In no particular order, it allows avoiding many programming errors, and it avoids project delays because the programming errors that maybe are discovered only during the testing phase cause project delays very often. MISRA compliance makes compiler qualification when required relevant, because as part of compliance with respect to MISRA C, you have to stick to the applicable language standards, and this is what the compiler qualification suites test for. Of course, it helps avoiding damaging people and other valuable assets. It helps avoiding litigations between acquirer and supplier, and in the end, it allows to sleep better, much better. So at BAGSang, we routinely conduct competitive evaluations between Eclair and other tools on customer code. So it is often the case that our prospects have already some experience, maybe they are using another tool, and then they want to compare our tool with the one they are using. So sometimes they involve us in these comparisons, and always under rather strict non-disclosure agreements, so I'm not allowed to share anything about this. In some cases, we have learned important things. We have found defects in our own static analysis platform. In most cases, though, we have found defects in the other static analysis platform. So here are the average figures when MISRA C 2012 is considered. So let us differentiate between cheap tools. They are sometimes integrated with compilers. They are not very good. So we found out that projects that are believed to be clean because these checkers have been used are found to violate 40 to 60 rules in MISRA C 2012. So these tools have false negatives for 40 to 60 rules. They also have many false positives, more or less around half of the rules, and there is no support for many or for all directives. Another categories are the expensive and more famous tools, and the situation is a bit better, of course, in this case. Projects that are believed to be clean because these tools presented no violations are found to violate 30 to 40 rules, so again, false negatives of the other tools, and they also present a significant number of false positives on around 50 rules. And some provide little or no support for directive again. So there are several structural reasons for Eclair's superior performance, and I will say something about some of them. First is the precise tracking of the pre-processing phase. Then Eclair gathers precise information on each translation unit, and then the information gathered for all the translation units are precisely correlated at link time or even at the end of the project to check whole program or whole project rules. Reason number 4, rules are checked with ad hoc checkers and not by composing an imprecise puzzle of microcheckers. I will say something about this in a minute. Most importantly, we have the systematic avoidance of configuration issue because Eclair interacts with the toolchain and it incorporates very precise built-in models of the toolchain. And then Eclair supports all guidelines, directives, as well as rules. Of course, for directives, Eclair needs some information to be provided in the configuration, but we never give up. We also give support to the users. So let us go through some of these key features. Precise tracking of the preprocessing phase. So some MISRA guidelines require reasoning on the code before preprocessing. Others require reasoning on the code after preprocessing. But others, again, require reasoning between the code before and after preprocessing. And some also require reasoning on the preprocessing phase itself. And this has deep consequences on tool presentation capabilities as well. So I will now show what I mean by this. I will use the Eclair static analysis platform. I have analyzed the project here, and here I am told that this code here is using the stringification operator, so the sharp operator. Of course, I cannot see it here, but Eclair is presenting me with a sequence of macros that are expanded, and in the end, I can see here the stringification operator just in front of alias, sharp alias. You see at the end of the line in orange. Okay, so this just to give you an idea of the importance of being able to look at the code before and after preprocessing and at the definitions of macro and so on. Then there is this thing about microcheckers that I mentioned before. So several tools support, to various extent, many coding standards. So they basically support all coding standards. They say we support this and this and this. How do they do it? They do it by, in fact, providing a collection of microcheckers that are juxtaposed to cover each individual rule. If you use one such tool, you will have seen identifiers, cryptic identifiers like 397S or 2790 or V1031. What are these? These are the identifiers for the microcheckers. What's the problem in this approach? The good thing, of course, is that you compose the microcheckers in different ways and you can cover more or less many different coding standards. The point is that the juxtaposition is often inexact. So in the picture, you can see the two red pieces. You can think of them as microcheckers. They are combined to cover the oval shape. This ellipsis, you can think of it as a MISRA guideline. So as you can see, the combination of the two microcheckers covers more or less the MISRA rule, but there is red stuff outside the oval shape, and there is white stuff in the oval shape. So what we have outside here in red are false positives, and the white stuff inside the oval shape are false negatives. So instead, in BAGSANC, we have chosen the hard and accurate alternative. In Eclair, we support less coding standards, maybe, certainly, but we support them with very accurate ad hoc checkers. And in most cases, the checkers are exact, meaning that there are no false positive and no false negatives. Another issue is tool configuration. So C and also C++, they are large families of languages. In C99, there are 112 implementation-defined behaviors. And since by definition, an implementation-defined behavior can be defined in two or more ways, there are more than 5 times 10 to the power of 33 possible languages. Actually, there are much more because two choices for its implementation defined behavior is very seldom realized. For example, choosing the integer and floating point types in the most common values brings us to more than 10 to the power of 36 languages. So for comparison, the Alexander star, which is this more complicated version of the Rubik cube, has only 10 to the power of 35 different positions. So this is relevant also because things are even worse. So a given compiler can implement via command line options several dialects of C. For example, the machine I'm using to give this presentation uses, it is equipped with GCC, for x86-64, and this version of GCC implements via option more than 1.5 millions of dialects of C. Okay, a consequence, the static analysis tool must adapt to the particular dialect implemented by the compiler with a precise set of options that I'm using for the build. And this possibly for each translation unit. I may use slightly different options to compile different translation units. So, and as a consequence, again, changing even one compilation option may have important consequences. So I have to remember, in most cases, to update the tool configuration to reflect this change of option. So we have seen many projects whose MISRA compliance was completely bogus due to the fact that the tool was not configured to recognize the precise tool implemented by the toolchain. One of the implementation defined aspects had to do with predefined macros. All compilers predefine a certain set of macros to a certain set of expansions, and many of these predefined macros are influenced by compiler option, which may be given on the command line, in environment file, variables, in configuration files. So if you fail to capture the predefined macros correctly into the static analysis tool, you may very easily have the wrong code being analyzed. So, and in our experience, in this competitive evaluation we have made with Eclair with respect to other tools, we very often found that the other tool was not correctly configured. So here we have several examples of dialect-dependent MISRA C violations. So just to give you an idea that this is relevant. So if you don't configure the tool correctly, you may have violations that are false positives, or you may not find violations, so you may have false negatives. With the Eclair static analysis tool, this cannot happen because Eclair automatically adapts to the toolchain with taking into account all the options you are using for the compilation of each translation unit. And in fact, what I'm showing here is one of the demo project which is supplied to people evaluating the Eclair along with the trial version of Eclair. So you can you will be able to double check what I'm saying here. So here, first example, it's dialect and library dependent violation for rule 1.1. So rule 1.1 of MISRA C 2012 says that you have to stick to a certain version, which you can select, of the C standard. Okay, so your compiler will typically implement one of the versions of the C standard, maybe C90, maybe C99, or maybe C11. Okay, so in this case, I'm showing violation in C90. This version of the library I'm using is in violation because for C90 the maximum nesting of conditional is 8, and this is exceeded in this version of the library I'm using here, which is GNU libc. However, for C99 and later dialects, the same limit is 63. So in this case, it's not exceeded. So I have a violation if the tool believes that we are in C90, and we have no violation if the tool believes we are in C99. And if the expectation of the tool is wrong, we may have a false positive or a false negative. Okay. Here is another dialect-dependent violation for Rule 7.2 that prescribes the use of a U suffix in case an integer constant is implicitly unsigned. So we have a violation on all implementations where int is 16-bit, for example, for compilers for the MSP 430, and no for dialects where int is larger than 16 bits. Here we have violations for rules in the series 10 that are present or not depending on the size of site T. Okay, for example, on native GCC on this machine, size T is 64-bit. So we have a violation. This line contains a violation of Rule 10.3, whereas if size T is 32-bit or even 16-bit, there is no violation. And you see that the situation is different for Rule 10.6. So in this case, we have no if size T is 64-bit or 32-bit, whereas we have a violation if size T is 16-bit. Let me see another example. Okay, so here we have again Rule 1.1 saying that we have to stick to a given version of the standard. This is a violation because on this machine with GCC, because in C90 long is not present. So it's if it is present, it is an extension. So we have a violation for C90, but we have not a violation for C99. Okay. So again, the things we have already seen. Now, direct dependent violation for Rule 21.1. It has to do with reserved identifiers. This identifier, decimal underscore DIG, is reserved in C99 and later dialects, but it is not reserved in C90. Okay, so we have a violation or not, depending on the language standard with which we have configured the tool, which hopefully is the same language standard implemented by the compiler with the options we are actually using for the compilation. Okay. Okay, this has to do again with reserved identifiers. Let us change topic. Directive 4.6 requires you not to use the basic data types like int, double, or long double, and it asks you to use type defs where the number of bits is explicit. Okay, but of course the number of bits should be explicit, but also should be correct. Okay, so it is okay when long double is really 64-bit, but it is not okay when long double is not 64 bits. Okay, so again, this is a dialect dependent violation. Okay, here we have another example, again on rule 1.1. In C99, it is permissible to have a declaration in this point of the function body. So after we add a statement here, in C99 is okay, so there is no violation, whereas in C90 it's outside the language definition, so it's a violation for rule 1.1. And this is similar here, so still rule 1.1, C99 is okay. In C99 we have bool, the bool type, and also we have underscore, underscore, func, underscore, underscore, whereas in C90 this is not standardized, so if bool is offered by the compiler, it is an extension, and same for func. Okay. So the final thing is the support of directives as well as rules. I wanted to show a small example of this using the Eclair static analyzer. So here we have already seen directive 4.6. Okay, so here we have in this version, in this build, we have built for with the mode such that long double is not 64-bit, it's more bit here. Now I don't know if it should be 96 in this compilation, but another important thing is this one. So directive 1.1. Directive 1.1 said that any implementation defining behavior on which the output of the program depends shall be documented and understood. And I said that in C99 there are, which is the language standard with which we are compiling here, there are 112 implementation defined behavior. As I said, Eclair always gives assistance. It tells us that we need just to document 10 of these 112 implementation defined behavior, because the program we are compiling only depends on 10 of them. For 6 of them, the dependency is sure, so the program definitely depends on 6 implementation defined behavior, and for another 4, the dependency may cause or not a different behavior of the program. Okay. Let me continue. From here, it's time to conclude this short presentation. So drawing from 10 years and more of experience in the field, we have selected some of the topics that have been more common in our day-by-day experience in working with prospects and customers that compared Eclair with other tools. So we have explained some of key things that you should take into account when you are choosing a tool for conducting proper MISRA compliance checks via static analysis. So there are several messages to take home from this short presentation. Selecting a high quality tool can make a very big difference. So it's really striking for us to learn that some of the people then turning to Eclair spent 2 months trying to configure another tool without succeeding. So this is something really striking. So, and in fact, a tool like Eclair that self-configures itself depending on the tool chain is invaluable. So it's a very major time saver, and most importantly, it gives you guarantees that your analysis results are relevant with respect to the code that you are actually running. Low quality tools easily cause totally meaningless results. So I have only touched upon the topic, for example, of predefined macros, but you have seen something about um, dialect dependent violation, and also they cause a waste of time. Waste of time because when due maybe to misconfiguration or to other tool defect, you get false positives, and you are not able to recognize they are false positive, then your engineers will waste time changing the code in an attempt to fix the violation, which in fact is not real. So, and in doing so, they will certainly waste time, and quite likely they also make the code worse. False claims of MISRA compliance are even more dangerous because you claim MISRA compliance and then maybe the acquirer uses another tool, and this can cause litigations or even worse if somebody is armed by defective software. So this is basically all I wanted to say, and if you have questions, I will be happy to try answering them.
Thank you, Roberto, for sharing how to overcome the real-time issues in today's session. We request all the delegates to drop your questions in the chat box now so that Dr. Roberto will answer your questions.